Okay, essential problem in planetary astronomy is to understand whether or not planets, moons, and so on that we study can retain internal heat. And if they do, they'll be able to build mountains and so on. So let's look at two examples, the Earth and the Moon, and we're going to ask a pretty straightforward question. Which one would you expect to more effectively hold heat in its interior? Generate that heat and hold it in the interior. And let's start with a kind of a basic question. Imagine that you look at the wall of a building, and the wall of a building has got two windows in it. We've got a heated interior. It's a cold winter day outside, and there's in one wall of the building we have a window that's this big, and in the other wall of the building we have a window that's this big. Common sense would tell you this window, this one right here, is going to lose a lot more heat. It's going to radiate a lot more heat outside. The interior of the house will become colder because it's got a large window that's going to shine heat out into the outdoors. Maybe you pull the window open. This one is going to let some heat out, but not much. And how much heat's going to come out? Well, it's going to be based on the area of these two windows. You know, if this window has a lot more area, this might be 5 or 10 times the area of this small window. It's going to let out 5 or 10 times as much heat. Just common sense. Okay, take a second step. And let's imagine something that you maybe haven't seen before, but suppose we somehow invented a weird kind of a furnace that we use to heat our rooms. And it's, again, a winter day. This time you're inside the house. And we're going to have two furnaces. And the furnaces are going to be large, warm balls, heated interior in the inside of the ball in some way. And the heat's going to shine out through the surface of the ball that's mounted in the room in some place. You know, I can imagine this working. Here's a large sphere, and here's a small sphere, okay? And I'm going to ask which one is going to be more effective in heating the room. Let's just say that we warm both of them. The interior are both 500 degrees. So they're identical furnaces. This is a 500-degree furnace. This is a 500-degree furnace. But this one has got a very small surface area. It's got a large surface area. The heat is going to shine out through the surface of each one, okay? And it's going to warm the room. And obviously, which one's going to do a more effective job of warming the room? Obviously, you're going to have a bigger furnace. And the reason it'll be more effective is it's got more surface area through which the heat can escape from the furnace into the room. Real easy. And we know what the formula for the surface of a sphere is, okay? It's 4 pi r squared. That's the surface area. And so, because the radius is larger in this one, the surface area is larger in this one, and it's going to generate a lot more heat, pour it out into the room, and more effectively warm the room. Okay, so that makes sense. We can see that pretty well. Let's take this argument a step further and realize that we've got to bring two things together in making this argument. Not only how effectively the heat from the interior of a planet is lost, thereby cooling the planet off, and it's not going to retain much heat, or we've also got to take into account that heat will be generated in the interior of the planet. So let's take both those into account, and let's deal first with loss. Okay, loss of heat is pretty straightforward, and what my argument will be is a planet that's got larger surface area is going to more effectively lose its heat, and therefore the heat retained will be lower. Okay, so that's an inverse proportion. Heat retained is inversely proportional to 1 over the surface area. Okay? Heat retained in the interior of a planet is going to be 1 over 4 pi r squared. And that would tell us that a large surface, a large planet like the Earth, will lose heat more effectively through its surface, and therefore will more effectively cool off. That effect is competing with another effect, and the competing effect is the production of heat. Okay, and the production of heat occurs in two ways, several ways, but one way is through the infall at the beginning of the history of the planet. Another way is through the amount of material in the interior of a planet that decays radioactively and generates heat by its decay. Larger amount of material in the interior is going to decay, produce a lot more heat. Larger amount of material in a planet is going to more effectively draw in new material during the formation process and generate a lot more heat by infall. So we would expect that the heat in this situation is going to be directly proportional. That's AT is going to be directly proportional to 4/3 pi r cubed. It's going to be directly proportional to volume. Straightforward. Now all we want to do is combine both these ideas, this one and this one. And combining them is just going to say the result is the combination heat combined into one equation is going to be proportional to 4/3 pi r cubed. And then in the denominator, the inverse proportion that we talked about with the loss is going to be 4 pi r squared. We don't worry about the small stuff. This is a really crude argument. Scientists often make an argument like this because they're interested in finding out the general run of things and not in getting a detailed correct answer. That takes a lot more work. And we've got r cubed up here, we've got r squared down here. That means that the r squared cancels out of the denominator. We don't worry about that stuff. That's telling us that heat is proportional to the radius of a planet. So to go back to our first question, if heat is proportional to the radius of a planet, the planet with the larger radius is going to retain more internal heat. The Earth is going to retain more internal heat than the Moon.